Hello viewers, welcome to this podcast. To effectively test and validate power electronics applications, you need a sophisticated simulation environment that can manage the special needs of high-frequency power systems, and ideally, one that includes the computational power of FPGAs. I'm pleased to welcome dSPACE Generic Tools Manager Katrin Whitting to this podcast. She is joining me today to explain how you can simulate power electronics without FPGA programming skills. Hi, Katrin, welcome.
Hi, Alicia, nice to meet you.
Nice to meet you as well. Katrin, in our last podcast that featured Thorben Hofstede, he told us that FPGAs are becoming mandatory to validate control systems for power electronic applications. Can you briefly recap why FPGAs are important?
Well, real-time simulation of power electronic applications is a quite challenging task. Power electronic systems act highly dynamic, as they typically contain several switching elements with high switching frequencies. On an FPGA, very small simulation times are possible using parallel computations. As a variety of topologies exist for power electronic applications, we can also use the flexibility of an FPGA to implement it for a wide range of applications.
Do engineers need to have specific programming skills to use FPGAs in real-time systems?
Well, it depends. Let me go back to the screen you've already seen in the last Learning Bits sessions with Thorben Hofstede. Here you see the radar chart again. There are different approaches with different advantages for power electronic simulations. First of all, there's a possibility of circuit-specific implementation, as it is also offered by our engineering service. In this case, deep knowledge in modeling, FPGA programming, hill simulation is required, but of course, extremely fast and precise models result. Another approach is to use ready-to-use models like XSG Electric Components library from dSPACE. In this case, they can be easily integrated into existing applications and less special knowledge is required, but the variety of topology is limited to the main use cases which are frequently used. To allow flexible topologies without specific programming skills, we developed the Electrical Power System Simulation Package, EPSS. This package has a generic FPGA model and allows to work with topology-based modeling.
Can you show us what the workflow for topology-based modeling looks like?
Well, the workflow for topology-based modeling with EPSS is quite easy. You just draw your circuit in SimScape Electrical Specialized Power Systems, formerly known as SimPower Systems, which is a MATLAB Simulink toolbox. EPSS contains an additional Simulink toolbox, which can be used with specific real-time simulation blocks. And the circuit data of the SimScape Electrical model then is put together in a so-called EPSS file, which contains all the information needed for real-time simulation on the FPGA directly. And by using this file, you can directly work with the FPGA. You don't need any time-consuming synthesis. You don't need any FPGA knowledge. It takes only a few minutes and you are ready to start with your real-time applications on the dSPACE systems. I will show you an example to demonstrate the workflow. Here you see the SimScape Electrical model of a push-pull converter. The dSPACE EPSS library, which is shown here, contains several blocks which help for real-time simulation. A very important block is the setup block, which allows you to configure the sample time, the solver type, the number of output iterations, which are important to directly include diode switching, and so on. Having configured everything, you have the possibility to export this model information to an EPSS file, as mentioned before, by this button. To check if your model is capable for real-time simulation with the EPSS setting, we included an analyze model function, which gives you information about your model and if it's possible to run this model directly on the dSPACE hardware or not. If it's not the case, some hints are given what you can do to get it ready for FPGA simulations. Having generated the EPSS file, you can use the standard dSPACE tools configuration desk and control desk for real-time simulation. So here in configuration desk, there's a specific extension included for EPSS, which allow to draw an EPSS on FPGA block into your signal chain. Then the EPSS file is chosen and all the specific properties from your circuit are directly shown here. So the switch gates can be configured, you can map the I/O, you can choose if they come from digital in or from some other hardware parts from the processor. To observe the signals during the runtime applications, you then use the dSPACE product control desk. Here we have also included a specific FPGA scope for EPSS, which allow to display the signals with an accuracy of down to 8 nanoseconds.
Can you use topology-based modeling in arbitrary power electronics applications?
Well, you can't make everything possible at the same time. FPGA-based real-time simulation of power electronics requires a trade-off between FPGA resources, modeling approach, accuracy, budget, and more. Caused by the generic idea of EPSS and the limited resources of an FPGA board, a trade-off was already made for that solution. So far, many relevant topologies can be simulated out of the box, and the applicability of EPSS is constantly widened from release to release and from current hardware platform to the next one. However, if the trade-off, which was made for EPSS, fits to the customer's requirements or not, is mainly given by the application under consideration.
Do you see simulations that use the dSPACE electrical power system simulation package as isolated solutions that exclude other approaches?
No, definitely not. At the beginning, I talked about different approaches, ready-to-use models, circuit-specific implementations, and EPSS. All these approaches can be seen as puzzle parts and often are combined to find the best solution for the specific application. The combination of these approaches is quite easy and has a continuous workflow using the dSPACE products configuration desk and control desk. Let me give you 2 examples.
Great.
Onboard charger, you usually have extremely high switching frequencies, which require ready-to-use models or even specific implementations by the engineering service. But even in these very challenging applications, there are parts of the model in which EPSS can be used perfectly and where you can benefit from the flexibility EPSS offers. For example, the input filters of the onboard charger, the grid, and the connection between onboard charger and grid can be perfectly simulated with EPSS. Secondly, back-to-back industry applications. Here you can use a combination of EPSS and ready-to-use dSPACE XSG electric components models. Therein, the grid and the active rectifier are realized using EPSS. The 3-phase inverter and the motor are simulated by dSPACE XSG electric components. If necessary, also a specific load, for example for a turbine, can be realized by our engineering service. So all the different approaches can be used in combination very easily, performing efficient real-time simulations on our dSPACE hardware.
Kate, thank you very much for speaking with me today.
Thank you.
Thanks.
dSPACE, your partner in simulation and validation.